Thank you. Okay, hello everybody. It's a great pleasure to introduce Dr. Christophe Benoit from the Nice Observatory to talk on galaxy clusters and cosmology. This is the last session before the closing ceremony. So I giving the stage to the Dr. Benoit. Here you are.
Thank you, Sinan. So first of all, I would like to thank Ayşegül and Orhan for inviting me to give this lecture. And I would like to apologize again for the not being able to contribute yesterday as it was supposed to be. Okay, so let's get started. So here are the few points I would like to cover in this talk. I will start describing a little bit what are galaxy clusters. You may not be all familiar with this kind of object. So I will describe a number of observable signatures and discuss the mass budget and the different ways to actually estimate masses of clusters. And this is a crucial ingredient for using clusters for cosmology. Then I will try to link in a very short, a very brief overview, link those objects to the more global theory of structure formation. And with this in hand, we can see how we can use in particular cluster counts to actually derive a number of constraints on cosmological parameters. So let's get started. So galaxy clusters are, well, just maybe one question. Can you all see the bottom of my screen? It seems that there are a number of things that are outside. I don't know, can you confirm, Sinan? Or?
We see the coma cluster in the bottom top.
You don't see what is written below.
Not the
okay, so it means that part of my image is actually cut a little bit. Okay, so I will take that into consideration. So galaxy clusters were actually discovered in the early 30s, actually right after we understood that galaxies were objects individual from the Milky Way. I mean, at least the spiral nebulae, as we used to call them in that period. And quite quickly, we understood that a number of those galaxies were actually grouped together in very large concentrations. And so actually, this is one of their main properties, and that gave their name. They can actually be collections of hundreds to thousands of galaxies. And as early as 1933, there were already relatively detailed studies on, for instance, the Coma cluster, which is the richest local cluster, okay, by Zwicky. And the immediate question was to understand, is this actually an object? I mean, are these galaxies there? Is it just a projection effect, or do they actually form a particular object, as we may think? Okay, so he studied the velocities of these systems using redshift measurements based on spectroscopy, and he found out that in Coma clusters, well, he was using at that time only a dozen of redshifts, but he found that these redshifts were actually not so close to each other, and he found the differences in velocities that were more than 1,000 kilometers per second. And so he really questioned the nature of the system. I mean, can this really be a bound system? Because this was like pretty large velocities. So if they have to be bound, then it seems that the mass carried by the galaxies is not actually enough to make it bound. So they may just be close to each other at a given time, but then escape, right? So actually, already at that time, he expressed the idea that maybe we can have missing mass in this system. Okay, so not dark matter as we would say today, but at least missing mass. And okay, we'll come back to that. So actually, if we look at the distribution of redshifts in the direction, so here you are missing the text below, which says that example of a redshift distribution in the direction of a galaxy cluster. So here you have an histogram, and you have the number of galaxies along the line of sight. And you can see that if you look in this, the direction of this cluster, you actually have a very strong peak at 75,000 kilometers per second. Okay, and if you, so which suggests that maybe you have a concentration of objects indeed more or less at the same distance. And if you actually zoom on this peak, you can see that you have a dispersion, and this is the large, typically the dispersions that Zwicky measured, where you have here 1 sigma, which is about 1,000 kilometers per second. Okay, and you have this very large dispersion here. So the way to the way to analyze this is that if you want to actually extract velocities, I mean, to interpret those redshifts, you may say that if the cluster is a bound system, then it is escaping from us following Hubble flow. And so if you take the median velocity of this cluster, you may subtract it, okay? So you remove the effect of expansion, and then you end up having a distribution of velocities, okay, which would be now actually the proper velocities of galaxies within that system, okay? And here we have only the radial component of those velocities. But from this, we can actually measure a dispersion, okay? And this dispersion is usually related to the richness, and we will see also to the mass. So how can we see that? Well, if a cluster is seen as a stable, self-gravitating system of objects, then you can apply the Virel theorem, okay? And if you do that on this kind of systems, you will have the kinetic energy that is going to be equal to -half of the potential energy. And if you derive the maths, you will end up here having a relation between the velocity. Can you actually see my cursor, Sinan?
Yes, we see it.
Great. So here you have the total mass of the system that is directly related to velocity squared, the average velocity. So here in our case, so you can derive that in 3D, but now if we consider that, okay, this is if it's an observed cluster, it's going to be projected. The velocities are going to be only radial components. And in that case, what you can do is to relate the total mass of the system to the dispersion of the velocity as we can measure from the previous graphs, okay? And so this leads actually to estimates of the total mass of those clusters that are of the order of 20 times larger than the typical mass, than the mass that can be carried by the galaxies themselves, okay? So indeed, the idea of Zwicky that there should be missing mass there is justified here. And it's by a large number, okay? So of course he did that study with a very few galaxies, but it's interesting to see that he already pointed out something that is fundamental about clusters. Here, okay. And indeed, there is missing mass because actually all the mass is not carried by galaxies, but for this, we had to wait much later. So here you are missing the text. On the left side, it's an optical image, and on the right side, you have an X-ray image of the coma cluster. And the right figure shows the presence here of a large amount of gas, okay? And so this is a second component that could be observed only at the end of the 60s and early 70s. Okay, so that's when, because, okay, to be able to observe an X-ray, you need to go above the atmosphere, okay? So first observations of clusters were actually done with by American militaries, okay? And then when they declassified those data, we actually had access to the X-ray sky, okay? But then, so this was the case with Virgo, which is the closest galaxy cluster to us. And in 1966, we had the first signal that was measured. In 1971, coma and Perseus were observed. And then the first satellite dedicated to X-ray observations was launched. And this, the PI was Giacconi, who actually got the Nobel Prize in 2002 for all his works in X-ray astronomy. And based on these first X-ray systematic observations, it appeared that at the position of galaxy clusters, as we could see them in the optical, we could actually measure a very large X-ray extent. Okay, and initially it was quite debated what would be the emission process of this, but quite quickly it turned out that this should be related to what we call thermal Bremsstrahlung. Okay, and what the thermal Bremsstrahlung is, it means that it's a deceleration radiation. So you have moving particles, typically electrons. They are losing kinetic energy, which is converted into a radiation. Okay, so due to the presence of a hot gas, you have this emission. Okay, of course, it's not clear. It was not clear at that time. When what is the origin of this gas? Was it there in the cluster from the origin? And so this was already questioned in 72. But we had to wait until 76 to actually be able to measure, to do X-ray spectroscopy to find out that in this gas, actually, you can actually observe X-ray emission lines from iron. So you have indeed a lot of hydrogen and helium, but you have also abundance of different metals. And this led to the idea that this gas was actually ejected from stars, as it's described in the seminal paper of Bacal and Sarrazin in 77. Okay, then I don't want to describe the whole X-ray astronomy. It's a very, very wide field, but just to mention a few surveys that played an important role for clusters. So there was a Rosat All Sky survey, and more closer to us, you may have seen a lot of very nice images from Chandra and XMM. And very recently launched is eRosita that is for sure going to bring us to a revolution in terms of clusters, but I'll talk more about that a bit later. Okay, so from the gas itself, we can actually, from the X-ray luminosity, one can estimate the mass that is carried by the gas. And here, typically, we have a mass that is 3 times the mass that is carried by the galaxies. So you said, as you see, we said that the galaxies were missing maybe 20 times of the total mass. But now with the X-ray, we actually show that we still miss a lot of mass, okay? And so here on this image, I want to show that the very good consistency between the localization of the galaxies, and on the right side, you have superposed the X-ray emission. So really at the central part of the cluster has a higher density of gas, okay? So you have a very nice alignment between those 2 observations. Okay, so from the gas, you can also derive a mass. And the way you do that is that if you assume that your system is in hydrostatic equilibrium with the cluster potential, then you can make equate these different energies and derive from the temperature. So the temperature of the gas is going to give you directly a link to the total mass of the cluster. Okay, so if you do that, you find also an excess of mass relative to the gas itself, which is consistent with what you would have using velocity dispersions, as we have seen before. Another way to tackle the problem of the mass of clusters is to use another technique, which is the gravitational lensing. Okay, so if you have an important mass in space, it can play the role of a deflector if you have background lights, and with equations that are quite similar to optics, as we see with lenses, as we see here on each side of this image. So on the right side, you have the blue arcs are actually correspond to a background galaxy that has been distorted, and can be seen taking with different shapes, and and that can be used to actually measure the total mass within the arcs. So this now, if I show this with a cluster, you can see here that you have many arcs in this image, and based on this, you can derive a total mass, okay, but only within the region where supported by the arcs themselves. Okay, so this technique is very interesting. So this is what we call strong lensing, because you have a very strong distortion of background light, and it's very interesting to measure inner part of the cluster masses. But it's not enough to measure the outer part, where the gravitational potential is not as strong, okay? And then we are missing a part of the mass for this. So we have the total mass, but only in the central part. But fortunately, we can use other techniques based this time on what we call weak lensing to actually probe the outer part of clusters. So the idea here is that if you have background sources, background galaxies, so it's not that they are randomly distributed as it's written here, but their orientations are randomly distributed. Okay, because these, if you have distant galaxies, there is no particular reason why they should have not random orientations. Okay, and so if you look at if you observe them, of course, the light coming from those background objects are going to be following different paths depending on the mass that could be on the line of sight. And the presence of this mass is going to change the shape and also the light, because the sources can be magnified and have different elongations and orientations. Of course, it's a very weak effect, so it's not clear to see on each individual object if they have been changed a lot from their original light distribution. But what you can do is to use this information in a statistical sense. Okay, so here you have a galaxy cluster where you can study statistically the orientation of background galaxies and compute the mean orientation of those objects around a cluster. And here what you can see is that you tend to have an orientation that is circular around this concentration of galaxies. Okay, so again, from this you can derive a total mass, and this time you are not limited to the central part. Okay, so of course the difficulty here is that you really have to be able to, I mean, you have to have very good images where you control the PSF and all kind of distortions that could affect your signal. You're really trying to measure something that is very weak, so it requires extremely good photometry. So the space is good for this, also from the ground, but you really need to control all your systematics. So these kind of techniques really, I think, well, developed a lot in the last 20 years, and future space missions that are dedicated to extragalactic astronomy, of course, are very interested in developing those techniques in a more systematic way. So Hubble Space Telescope did a lot of, I mean, helped a lot in this kind of studies. But for instance, with Euclid that is coming, the idea is to be able to do that more systematically on much larger regions of the sky. Another interesting technique to observe and derive information about clusters is what we call the Sunyaev-Zeldovich effect. So this is an interesting thing. I mean, here you have the idea is that you are going to use the photons from the cosmic microwave background because these are going to be affected by the presence of concentration of hot gas. So here you have on this diagram the surface of last scattering. Okay, so when the cosmic microwave backgrounds are emitted, and if some of the photons intersect the presence here of a cluster, then you will have a scattering of these photons, which is an inverse Compton scattering, which has the property to actually give energy to those photons, and the electrons of this concentration on their side are going to lose a bit of energy. Okay, so this is it's interesting because you can, if you compare to other photons that are not going through such systems, then it will you will see a difference in their energetic distribution. So this was predicted by Sunyaev and Zeldovich in the early 70s, but it's something that we it's a technique we're using for clusters only since well, basically Planck, I mean, in a bit earlier, but it really exploded with the Planck survey. Okay, because you need to observe in the millimeter, but you also need to have a good resolution to be able to really trace those systems that are quite small scales. Sorry. So this is the spectral signature of this effect. So you can see here on the left side, you have the CMB spectrum that is represented here in dashed line. But if you look at the photons of the CMB that are going across a cluster, then you have a shift here. Okay, so now if you subtract one by the other, you will have here a characteristic curve that you can use to actually detect identify the presence of a cluster in a given line of sight. Not only that, but you can actually use the intensity of this decrement that is coming from the difference between those two curves to actually infer what we call here the Compton Y parameter, which is actually proportional to the density of electrons and also related to the temperature of your system. And now if you integrate that over the whole cluster, you can actually derive total energy that can be used as a very good mass proxy. So it's another way to actually determine the mass of a cluster, which is widely used nowadays. Okay, so here are some images where you can see on the right side, you have X-ray images. And on the left side, you have for the same cluster, the Planck observation. So using this SZ effect. So you see a very, very good consistency of those distributions. With in the middle, you have basically a hole because this is the decrement of those CMB photons. So it's not seen as an emission, but more as it's kind of shadow. Okay. Okay, another very interesting thing here about SZ effect is that as it acts, the clusters act as a shadow on the CMB. What happens is that they are actually not affected by the usual dilution of emitted radiation and to the 1 plus Z to the minus 4 cosmological surface brightness dimming. Okay, so as you don't have any dimming, your object, whatever the distance it is, you will see it exactly in the same way. Okay, you have really a compensation of the dimming, and it means that you can, in principle, detect clusters at any redshift. Okay, so here in this image, you can see what happens if you observe. Here you have some clusters that are observed in X-ray. So you have in the bottom left of each panel, you have the X-ray image, and you can see that when the redshift, which is here on the right, for instance, 0.83, quite high redshift. In X-ray, you have almost no signal, okay, and you have a strong signal at low redshift. But for the SZ, it's exactly the same, right? So that's a very promising technique. So of course, it's this is in principle because you have also issues related to the resolution. But I mean, in principle, you can really detect if you have a rich cluster, you can detect it at any redshift. And that's the only kind of observation where you can do that because, I mean, for concentration of galaxies, we are going to suffer from problems that are similar to X-rays. Okay, so now if we wrap up all this with this, I mean, on this image, you have the Able 383 cluster with observed with HST plus the Chandra in X-ray that are superposed. Okay, so the typical mass of galaxy clusters are of the order of 10 to the 14 to 10 to the 15 solar mass. Their typical sizes is a few megaparsec across. And so these are definitely the largest and the most massive bound systems in the universe. But they are also extremely rare. Okay, so observing them requires usually to have, I mean, to cover large areas of the sky. So they are composed mainly. They are composed by galaxies as they were discovered, but this is only 5% of the total mass. By gas, 15%. And then the rest is made of something else, which is, something that is not, that plays a role in terms of gravitation. So we can actually see it in the distribution of velocities of galaxies or using gravitational lensing, but it's not baryonic matter, it's a matter of a different type. Okay, so here we have most of this mass composed of dark matter. So now, maybe just before continuing, there is an interesting target that a lot of you may know, which is the bullet cluster that's been used to actually to prove that this dark matter actually exists. So how can you read this? So in blue, so first you have here an image where you see a lot of an optical image where you see a large concentration of galaxies, and you have actually two clumps. Okay, so one is here and the other one is here. And superposed, you have in blue the gravitational lensing signal that is really superposed to the distribution of galaxies themselves. And you have here in pink, reddish, you have the distribution of gas with this very interesting feature here where you see a cold front, okay? And this is really exactly what you would expect when you shoot a bullet, okay? So the way to understand this is that you have two systems that are interacting, okay? And more than that, you have a merging of two clusters with this small component that actually crossed the big one here from the left to the right. And in this process, the gas, because of friction and collision, actually was left behind, whereas the galaxies and the dark matter, they can continue their way as being collisionless. Okay, so of course this system is going to go back to equilibrium at some point, but right now it has been caught exactly when the gas is basically displaced, is moved relative to the centroid of the dark matter and the galaxies. Okay, so that's it's a very, I mean, it's difficult to observe this kind of system, but I think it's.
Oh, we are here, no problem. It was a
Okay.
mistake, I guess. Okay.
No problem. Okay, so this cluster was actually a reference for proving the existence of a component of matter that weights a lot but does not interact. Okay, in the same. So nowadays we are lucky to have so many kinds of instruments and observatories to actually cover many different wavelengths. So here in the center, what you don't see is this is the Planck satellite. So Atacama Cosmology Telescope, for instance, is dedicated to the SZ effect that I mentioned before. Also the South Pole Telescope. You have the optical. You have here Chandra. I mean, we're covering a lot of wavelengths that are that can allow us to study clusters, for instance, with many different perspectives. So now let's turn to the formation of clusters and see how we can link them to cosmology. So for this, I need to go through a little bit of a theory of structure formation. But before getting started, let's look at those two images. So these are two observations that we have. So the one on the top is the cosmic microwave background coming from Planck. Okay, and here you have temperature anisotropies that are given by those two blue and reddish colors. And this was a signal. So this is a signal that was emitted at a redshift about 1000, okay, when the universe was 380,000 years old. And at the bottom, you have the local distribution of galaxies, so at redshift around 0. And so these two images tell us something about how structures evolved, okay? Because on the top one, so you do have structures that have that correspond to fluctuations of the order of 10 to the minus 5. So let me first introduce this quantity delta, which is the density at a given location minus the average density and divided by the average density. Okay, so this is a contrast, a density contrast, and this delta for in the case of CMB is around 10 to the minus 5. Whereas if you look at galaxies, for instance, you would have typically a delta of 10 to the 6 or clusters less than that. And the idea is, okay, how do you go from this to here? Okay, so what's the relationship between those fluctuations when in the early universe with those objects that we can observe locally now? So the idea here is that you would go from one to the other based on the amplification of the gravitational processes. Okay, so so the idea is the following: is that if you have a small overdensity at early times, as you would see here, let's say that this little bubble here is a small overdensity. When the universe expands, because you have a little excess of mass, then, well, this little bubble is not going to expand as fast. And at some point, it's going to well, its own expansion is going to decrease, and at some point it's going to stop expanding. So universe will continue, but this bubble is going to start contracting and eventually collapse to generate an object during the cosmic time. So that's the idea here. So to continue on this, we need to get some. We need to go through a little bit of the equations of the homogeneous universe, which are based on the Friedmann-Lemaitre equations. So these describe the average evolution of the universe, where you have here A, which is the scale factor of the universe. So here this quantity is just the Hubble constant, okay, or the Hubble value, A dot over A. Okay, and these equations derived from GR actually tell us under a number of assumptions, and the main one being that the universe is homogeneous, is that it will tell us how this A factor, the scaling factor, how it's going to evolve in time, depending on the content of the universe. Okay, so in these equations, you can notice here the K value, which is the curvature. You can notice here the presence of a cosmological constant. Here, rho is the density of the universe, and you may have pressure terms here with a P. Important points. So we can define a critical density, rho C, which corresponds to the case where there is no curvature. Okay, and usually we define the densities as a ratio to the critical density with this omega quantities that I'm going to use following in the next slides. And here you have H, the Hubble constant, which is A dot over A. So based on this, we have, and on our observations, there are three main periods in the history of the universe. There is a first period where we are dominated by radiation at very early times. Then we have a period where we are dominated by matter. And finally, more recently, dominated by dark energy. So here we have a first interesting moment, which is the radiation matter equality, okay, which corresponds to a redshift of 3,500. Then there is another interesting time, which is the decoupling when the CMB signal was generated at a redshift of 1100. So let me see, I'm missing something here. I'm sorry, I have a slide missing. Excuse me, I have a slide missing. I don't understand where it is.
It's okay, thank you.
Just a second.
Sure.
I don't know why it's not shown, but it's, okay, I see why. Sorry. Okay.
Can be a hidden slide or something.
Yeah, they were. I don't know why, but they turned to be hidden. So I'm going to.
Maybe you can check show all slides or something.
It is fixed, so I'm coming back. Just a second.
Okay, perfect.
Yeah. Okay. Okay, so to understand the growth of matter over densities, I think it's interesting to look at. Can you see my screen again, or by the way?
Yeah, we see perfectly, no problem.
Okay, good. So this is a simplified, very simplified scheme, but I think it's very pedagogical. Is that okay? If you take an overdensity that is a spherical top hat, so you have a sphere with a constant density of with rho b, okay, and the universe has a density of rho a, okay, and so rho b is larger than rho a, okay. So what we will assume here is that we are in the linear regime, okay? So we are at early times, and so what's going to happen is that this little bubble, as I explained before, is going to grow, but not as fast as the expansion, okay? So we can actually consider these two. I mean, we can write the Hubble, I mean, the Friedmann-Lemaitre equations for those two systems. Okay, so the bubble can be seen as actually as a mini universe that has a density that is slightly larger than the critical density. Yeah, and so rho a is supposed to be the critical density. So if I write the equations, there is no pressure, there is nothing, just a matter over density, and the equations can be reduced to these two. Okay, so you have this additional term that is coming from the curvature, because here you are above the critical density, so you have a curvature term for the first one. So what you can do is make the subtract one by the other. Okay, and you can, as it's the linear regime, so you can actually from this compute delta here as being 1 over b2 times rho a, and this is approximately a. So you can just with a simple computation show that delta should be proportional to a being the scale factor of your critical universe. Okay, so from this, what you can see is that your bubble is going to grow. I mean, the density, the contrast is going to grow, but in proportional to A. Okay. So what does this mean? Now, if we go back to our scheme before, so here the universe, when you go from CMB to now, had a scale factor that was multiplied by a factor of around 1,000. Okay, so if you have fluctuations that are of the order of 10 to the minus 5 at that time, multiplied, you will multiply this number by 1,000. Okay, and basically you get to 10 to the minus 2 when you are at z equals 0. And this has to be compared to the kind of objects we can observe now. So you see that this schema where you let those fluctuations grow under gravity, I mean, you don't even reach the nonlinear regime, so you don't actually form objects. Okay, and so this is a big issue. So of course you may say, okay, maybe those gravitational instabilities should start earlier. Okay, however, I mean, with normal matter, it's going to be difficult. Here you have the baryonic. You have distributions of matter before and after decoupling, okay, at the time of CMB. On the left side, you have this hot plasma, okay, just before finally light becomes, the universe becomes transparent and let light go, okay. But at that time, before decoupling, baryons are interacting with photons, and any fluctuation is not going to grow. I mean, here you have actually oscillations in the baryonic distribution, okay? And so you cannot have any fluctuation growing before decoupling, at least made of baryons. So now, to be able to go a bit further in this, to try to understand how this can be solved, let's see how we can, I mean, how the problem is solved in a more general way. So I'm not going to go through all the steps, but just to give you the main, the starting point and some of the main results. So the idea to solve this problem properly is to start from the fluid equations in an expanding universe. So we are going to start with the usual equations of continuity Euler-Poisson plus an equation of state. And we can solve this this system in an expanding universe by okay, we can say that we are interested in solving and find okay the evolution of the density. But we can, I mean, here we can develop this around and look at small perturbations around the mean density and understand how this delta here do evolve. So if you have delta that is much smaller than 1, you are still in the linear regime, okay, and you can treat that more or less analytically. Otherwise, if you want to solve these equations, you have to go through a numerical treatment. Here I'm also introducing the sound velocity, cs square, which is the derivative of the pressure to the density. So if you solve this system and look at the evolution of delta here when delta is very small, you end up with a general equation that is this one. Okay, so this is for a non-relativistic fluid, but you see here the differential equation that delta has to follow. So here you have, I mean, here you may recognize the Jeans equation, except that we have an additional term here that is proportional to delta, the first derivative of delta, and here you have the H Hubble constant, okay, that comes here. So it acts this acts actually as in a way that it suppresses the growth of perturbation. On the right side, you have a term that tends to favor the development of gravitational growth, and here you have a pressure term that goes against perturbation. Okay, so usually, so to be able to solve this, what we do is that we go to Fourier space, and this is interesting because in the linear regime, the different modes actually evolve independently, and now we can try to solve this equation. So to solve this equation, you see that there is a particular case when this quantity is negative or positive. Okay, and we can introduce here now the Jeans length, which is 2 pi over k when this quantity equals to 0, and it gives you a particular scale to your system that is given here. So for a static universe, so if you remove this quantity here, you will have two different kinds of solutions to the system. If the lambda is less than Jeans length, then omega square is positive, and then you have here oscillations. Okay. However, if it's positive, then this quantity becomes negative, and you get an exponential decay and growth. These are the possible solutions if you remove the Hubble, the expansion of the universe, basically. Now, for an expanding universe, it's a bit more complicated, and you will have solutions that depend now on the era. So if you are in the radiation period, the matter era, or after decoupling, and it will depend on the type of matter that you are considering. Is it baryonic matter or a matter that would be collisionless? And then, of course, it also depends on the scale, okay, which means the sign here of this omega square quantity. Okay, so if we solve this equation and we are interested in solutions, for instance, without pressure, so if you cancel this term, okay, and you are solving this after decoupling, then we can recover the fact that fluctuations grow proportionally to A, which is the scale factor. Okay, so we recover the simple solution that we had in our basic model just before. But now, if we are interested in the okay, let's look at the solutions in a more general way. So here you have in this plot, you have on the x-axis basically cosmic time, which is here indexed with the scale factor, and on the y-axis you have the amplitude of delta, the value of delta. So here you have delta equal 1. So here basically you are in the linear regime, now nonlinear. So let's assume that we start with very small fluctuations. So when those fluctuations correspond to scales that are larger than the Jeans length, in that period, this means that they are larger than the size of the universe. Then they grow. So matter fluctuations just grow until they become smaller than the size of the universe. Okay, they become, well, they correspond to scales that are less than the gene scale. At that time, they start to oscillate. Okay, so you have this stagnation period until we reach matter era. So in the matter era, now we will have two different types of behaviors. If you consider the usual baryonic matter, in this case, it's going to continue to oscillate because you have this coupling between radiation and baryons. However, if you have a collisionless component of matter, at that time it will start to grow, okay, and it will grow. It will grow independently, okay. Now, when we reach the decoupling, what happens is that the collisionless matter can continue to grow, okay, whereas the baryonic matter itself, actually just before decoupling, is going to even decrease due to an effect called the silk damping, okay, and this is due to the fact that the CMB photons are not emitted immediately, but there is a fraction of time where you start to have your photons are basically decoupling, but they are destroying all the smaller scale structures. Okay, so you have fluctuations here that are decreasing, and if we had not this component, it would be very hard from fluctuations coming from baryons to actually grow into any kind of structure. However, and this is where the collisionless matter plays a crucial role, is that this component is growing here, and so the baryons can actually fall into the fluctuations created by this matter, okay, and then get to the nonlinear regime at a time which is much earlier than what we could do before. Okay, so if these fluctuations had to start from the decoupling period, we would not be able to create objects. But because this collisionless matter is able to grow much earlier, then we can have matter fluctuations with the baryons that actually form objects. Okay, so here you enter, so this cannot be traced analytically, but you can actually construct here objects, okay, that are going to virialize and generate what we call here a dark matter halo with baryons that fell into it. So it means that this dark matter or collisionless matter is actually driving the fluctuations and driving the baryons. So the growth of fluctuations here are dominated by dark matter, okay, which in this case means non-collisionless matter. And the nonlinear regime and the structure collapse can start early enough now to generate observable objects within a Hubble time. Okay. However, we should say that the mass of those dark matter particles plays a very important role and can lead to very different scenarios. Okay, so not only we need to have non-collisionless matter, but it also has to have some particular properties that can allow for the mass distribution of objects that we see today. So in particular, for instance, if you consider dark matter particles that are relativistic, so what we call hot dark matter, in that case, we have very light particles with velocities close to c. And then we have an effect that is called the free streaming damping, okay, in the sense that those particles can escape their velocity distribution inside a clump is going to be, their velocity distribution is so high that the smallest structures are not going to survive in this process, okay? And so the smallest dark matter fluctuations are going to disappear. And so this is illustrated in this graph, where you see three types of dark matter. So you have the time that goes from left to the right, and three types of dark matter, so meaning different types of masses, okay? And what you see is that the small scale objects are not visible here when you consider hot dark matter. However, if you consider now more massive particles of dark matter, you will see structures here at all scale, okay? And if you let time go, you will start to see smaller scales in the hot dark matter scenario, but they're going to appear later. Okay, so here what happens is that you have a fragmentation of large scale structures when you go from in this hot CDM scenario, and in the cold one, the large scales are going to shape up by the aggregation of smaller structures. Okay. So with a hot dark matter, you have what we call a top-down scenario, where you have like first large structures forming, and then smaller ones created in time. Whereas with a CDM, it's going to be the opposite. You start from small ones that are going to aggregate and form larger structures. So dark matter here plays a fundamental role at different scales. So I didn't talk about it, but I assume you know that galaxies, the rotation curves of galaxies are actually, show that there is a presence of missing matter, dark matter at the scale of galaxies. Clusters, we already mentioned that at the beginning. And now we can see that for forming structures in general, we need actually this non-collisionous matter at all scales. So the main properties is that it should be a matter that is not interacting with electromagnetic radiations. It should be collisionless, and it should be rather cold, because if it's hot, then we don't create galaxies, for instance, early enough in the history of the universe. So this is the result of a numerical simulation that is based only on dark matter, cold dark matter, okay? And what you can see is that you have here the density contrast that increases in time. And you have the formation here of filaments, and here very contrasted at the nodes, at the intersection of filaments, very dense structures that appear in this diagram. Well, actually, if you want to show this this cartoon, we should rather show it in this way, because you have actually expansion going on at the same time. So you have this competition between expansion and gravitation, but in time this generates this very complex topology at large scales with voids, walls, and filaments, and so on. What is interesting is that, so here you have a simulation only with dark matter, but if you now compare the even by eye here, this dark matter distribution on the left side, and on the right side, for instance, the LEAK catalog, which is an observed catalog from the late 60s, then you really see that you have very similar distributions, and you can quantify this and show that statistically these distributions, at least on larger scales, are completely equivalent. Okay, so this shows that indeed a purely dark matter universe reproduces very well large-scale distribution of structures as we observe them. Okay, so now within those distribution, you may identify and count objects that form. Okay, because you may have some prescription. You know that when you have some objects are going to collapse in virialize in those simulations. Okay, and you will have objects appearing at different scales. Okay, so for instance, here on the right side, I circled a number of points where you may have, for instance, a cluster forming. Okay, and still connected to this cosmic web, but you definitely have some objects that are here independent from the Hubble flow. I don't know if anyone wants to ask a question in between, as you want. I mean, we may, because I continue. I don't know, Sinan, or if we wait for the end, or.
Yeah, and generally they ask.
May I have a question?
Oh, okay. Yes, please.
Okay, Christophe. So you are saying actually the formation of galaxies, or let's say complicated structures, relatively late. Let's say redshift what 10 or something. You know, late.
Yes.
Yeah. So this actually, let's say, confirms the so-called lambda CDM model.
Yes.
Because these are actually this assumption of the lambda CDM model gives you the initial conditions for forming the pre-galactic stars.
Well, I think that here I have not talked so much about lambda so far, but the dark energy actually plays an important role only at the end.
Yeah, 0.7 something, omega 0.7.
Yeah, exactly. So it's not crucial.
So it means that actually the formation of galaxies at small z redshift means there must be a phase before, after the dark age, where actually object like stars have been formed.
Mm-hmm.
And this is what the PhD going on here with my student.
Okay, interesting.
Yes. So because you have to have, yeah, actually this is funny. Why is the cold dark matter preferred?
Why is that? Sorry.
Yeah, why the cold dark matter is let's say it's not hot or not warm. Why is it better?
Why is it better? Because it can form objects earlier, small objects.
Object earlier. Otherwise, you have to. No, if you have hot, you said your galaxies cannot be formed earlier.
Yeah, that's true.
So therefore, the cold dark matter allows you to form object between the end of dark age and the galactic formation.
Yes, absolutely, exactly.
Okay, thank you.
That is why it's preferred, indeed.
Yes.
Okay, so now if we want to quantify, I mean, so let's assume that in those simulations we can count the number of objects that appear, and we can actually compute their mass by being the sum of the dark matter particles that are part of these objects, and one may derive a mass function. Okay, so the number of objects of a given mass at a given period. Okay. And we want to compare that to what we actually observe. So actually, we can also predict directly we can predict directly the halo mass function directly from a very simple model that was developed in the 70s by Press and Schechter, and then there were extended version of this work. But this is based on what we call the spherical collapse model. Okay, and what is interesting here is that based on this model, you can predict when you know the initial condition of a fluctuation, you can predict when this object at a given scale is going to collapse. Okay, just based on the fact that you have, well, okay, so you have the amplitude of your initial conditions, and you also assume that it's a Gaussian random field, and you let this system grow in time. Okay, and what they found out is that when you have a delta that goes above some critical value, okay, then you know that at that time the object is going to actually collapse. Okay, and you know the fraction of systems that are going to collapse. So this is only based on considerations on the linear theory, but you can actually use it to extend and make some predictions on what happens in the nonlinear regime. So this particular formalism was extended, and okay, I will show you results in a few minutes. Just what I want to say here is that these predictions actually depend on a number of quantities, and these are the quantities on which galaxy clusters can actually put some constraints. So dark matter halos of different masses or size, okay, they will appear at different epochs, and this depends mainly on a number of parameters. The first one is the amplitude of the power spectrum, which is basically the normalization that is the normalization of the power spectrum. Okay, that will give you the total number of objects if you want. It depends on the type of dark matter, if it's cold, warm, or hot. It will depend on the omega m, which is the density of mass in the universe, and also depend on the dark energy equation of state. Okay, so here is a comparison between the predicted and the measured halo mass function. So this is done only in the simulation. There is no real data here. You have basically the prediction of a model with the objects that you can count in a dark matter simulation. This is from Millennium. You are missing the reference that is below your screen, which is from Springer in 2005. And so here you have basically so you have on the x-axis, you have the mass of the halos, and you have a density on the y-axis. And what you can see here is that at different redshifts, so at redshift equals 0, you generate here systems of masses larger than 10 to the 15. And when you go back in time or with a larger redshifts, of course, the only halos you have here are the ones that corresponds to very low masses. Okay, so this is a CDM. Okay, so indeed at high redshift you have a cut and you cannot generate massive halos. So here you have two models. You have the first original paper from Press and Schechter, but so it gives interesting results, but it's a little bit off compared to the model. But there is an extended version of this formalism that is based on the fact that that halos don't form in a spherical way, but they can follow an ellipsoidal collapse. Okay, and if you consider that, you see that you get really close to what you can to your data. Okay, so this model works very well. This is another prediction here. Now you have the redshift on the x-axis. So this is from Moe and White 2002, and here you have the density. So and here now each line corresponds to mass of halos, 10 to the 7, 10 to the 8. Okay, so the halos of 10 to the 7, you can see them all the way to redshift 20. Okay, but the massive ones, so for instance, if you are interested in clusters that are more massive than 10 to the 14 solar mass, then you would expect them to find them appearing at redshift 4, but not later than that, right? And 10 to the 15, like the Coma cluster, for instance, well, you would not expect to find these kind of systems way beyond redshift 1. They really formed much, very early, much later in the history. Okay, so these are predictions, and we can compare some formalism, some models with numerical simulations and show that we have good tools in hand to actually describe what we can expect in terms of number of halos. However, we don't observe halos. We don't observe this dark matter. I mean, the dark matter is not observed directly. It's, you can find its some evidence of its presence, but you don't detect those systems directly as dark matter, right? And you need now, if you want to make a connection between these models and your observations, we have to make a link between these dark matter halos and clusters. Well, this is a nice image from a simulation where you see the how objects actually appear in the cosmic web that is traced here by dark matter, and you see that we have a sampled vision of this web with the observed objects. Okay, so fortunately we have now access, as I said, to many different kinds of instruments at different wavelengths to trace galaxy clusters. So we may use different signatures to detect them. So you may see clusters as being big concentrations of gas and use X-ray telescopes, concentration of galaxies and use optical imaging, or the SD effect with millimeter observations. Okay, so all these observations can be used to try to build and count clusters in our universe. But you see immediately that there are a lot of issues if you use one technique or another. On the top left, you have here a section of the dark energy survey, where you see that in 10 square degrees, you have now 1 million galaxies and up to I-23, and finding concentration of objects of galaxies here can be a tricky game. Okay, you may have a lot of projection effects. So of course you may have estimates of the redshift of the object, but usually you have only what we call photometric redshift, so poor approximations of redshifts. And so this means that detecting a cluster here is bound to to also false detections and so on. Okay, so you need to be able to quantify this. On the bottom left here you have XMM Newton that is observing the cosmos deep field, where here again in X-ray, of course, you suffer less from projection effect compared to what we had in optical. But there are other issues. You may be contaminated by the presence of point sources in X-ray, and many other different issues. Here on the right side, you have the millimeter observations, where clusters appear as a whole. As I said, it's like a shadow, right, on the microwave background, and so you may have holes here that corresponds to actual clusters. However, here also you may be affected. You may have problems of resolution. You may be affected also by point sources, and so on. So each method actually has different kinds of problems. So the most interesting thing here is to try to be able to combine them and compare and try to understand the selection function, because everything now, I mean, the game here is to be able to detect. You want to count clusters and compare to theory. So you have to have an idea of what are the systems you're missing, how complete are you, how many false detections are you making, and you have to do that in a statistical way. But having a good control on all these things is the tricky part of the game. So what does it mean to compare now with theory or with expectations? What you want to do is to build a model to say what you would expect with a given data set, what you would expect to count. Okay, so here in this case, what you would say is the following. You have here a theoretical mass function. So that's the ones I showed you before, for instance. So in a given cosmology with particular type of dark matter and so on, you would have here some theoretical mass function. And now you are going to plug in to say, okay, what you expect to observe is this thing, if you assume that cosmology, multiplied by a number of observables. Okay, so this is what we call the selection function. And that takes into account the completeness of your sample and the purity, okay? And here you have also the relation between the observable mass, the one that you are going to derive, given the true mass, okay? So here now we have to make this connection between the mass, because here in this expression we have the mass of the halo, okay? So we don't measure the mass of the halo, we measure some kind of mass and we want to relate it to the halo. So to do that, this is a very critical step, which is the what we call the mass observable relation. So we are missing again the lower part of my plot where it's written mass. So here in this plot, you have the observed quantity on the y-axis and mass on the x-axis. And you try to derive this relationship based usually on a small subset, because you are working with a big survey, but to be able to measure precisely the mass of systems usually is something you need so much additional observations that you can only perform on a small subset. Okay, so you try to find some what we call a scaling relation, okay, between your observed quantities and the mass, and based on that you are going to you build a recipe to assign to each cluster in your sample mass. Okay, so in general, this observable mass relation, so as I said, is going to be calibrated where you use a high quality X-ray, you're going to use weak lensing or spectroscopic follow-up. And you want to do that, of course, you want to have a sample that is as representative as possible. But depending on the methodology that you are using, you may introduce in this step a lot of issues. I mean, because you have to make assumptions on your clusters, but clusters are not as regular as halos. And you may actually use clusters that are not enough at equilibrium, okay, which is going to affect the distribution of redshifts or affect the distribution of X-rays. And you may have also all kinds of biases due to weak lensing with different kinds of alignments that can bias your estimate of the mass and so on. So this calibration of the scaling relation, moreover, is going to be statistically biased by the fact that usually you can estimate the mass for systems that are often more massive. Okay, so and when you want to include in your system, in your sample clusters that are less massive, these ones are less constrained, and so we have to make a number of assumptions here that that may bias the final results. So just to say that there are lots of issues on the way. This is okay. So that's these things you have to keep in mind when you make this comparison. This is just to give you one example of what can happen when you here you have dark matter halo, and you see that this halo is actually connected to the cosmic network. Okay, and you may have infalling material. And so this shows that, well, even at the dark matter level, you may be out of equilibrium in the sense that suddenly you have a group coming in, or you accrete continuously matter. Okay, so these kind of perturbations can sometimes lead to putting yourself out of equilibrium and bias your estimates. So this is something you see not only in the simulation, but here you have observations with Suzaku in X-ray. And you can see here, and in the background, you have optical image. And so those two stripes that you see here, those colorful stripes, are X-ray observations where you see at the center, you can see the central part of the cluster, but in the periphery, you have lots of little clumps that are infalling, okay, and are going to feed the cluster that is growing in time. Okay, so if you have to be careful when you estimate the mass of a system that you don't have strong perturbation coming from these kind of accretions. Now I would like to give you a number of some results that were obtained in the last well, basically in the last decade. I mean, of course, there are papers dealing with this number counts and cosmology, well, since a few decades, okay, but they are usually related to very small samples. And I would say it's only since basically the last 2 decades that we have samples that are big enough and with well-controlled systematics that the field really well, could extend, right? So in particular, in the optical data, the survey that played a very important role is the SDSS that started early 2000s. But here I will just present you some results that were the first actually results with SDSS in this cluster counts is from Rosso in 2010, and another one using X-ray sample in 2009. So these dates are interesting because they could compare directly with the expectations coming from WMAP. Okay, so WMAP started measuring the CMB in early 2000s. Okay, so in 2010 we had the final release of the cosmological constraints of WMAP, and they can be compared with the expectations from cluster counts. Okay. Then I will show what happened in more recently with the Planck at the period of Planck, and some very recent results. So here, let me show you, okay, what were, so here first, you have here on the left side, based on X-ray data, you have the number counts of clusters as a function of mass. Sorry? I couldn't hear. Is that a question?
No, go ahead, Christoph. It was a mistake of someone.
Okay, no problem. Okay, so on the left side, you have the number counts in 2 redshift slices. Okay, so here at low redshift in black. Okay, so you have the number of the density of clusters as a function of mass. Okay, and here at a lower redshift. So the first thing here is that this is completely consistent with the main constraint that are given since well, since at least 20 years, where you have here, or since even before, I mean, when we started introducing omega lambda. So here you have a universe with a cosmological constant of has a density of 0.75, the matter 0.25, okay, and you see those model with the counts, and you have a very good consistency between those two things. I want to stress here that it's this is not obvious, because you have you compare with cosmological parameters usually derived very precisely from CMB experiments corresponding to very high redshift, okay, and we want to compare with experiments at very low redshift. So I mean, if we need to have something completely, our model has to be consistent enough, and it's not obvious that you can go from one to the other, okay. So here I should say it's quite remarkable that if you use if you look at the WMAP result at that time, they are completely consistent with these, okay. Well, of course the error bars are large. They are large. I mean, here they are not given, but they are large both from the clusters, and also WMAP had quite large errors that decreased with Planck more recently. But the conclusion of this paper, as you will see from the one from the SDSS, is that basically you have a good consistency with WMAP. So we have experiments at two different times of the universe that are consistent, and it's very reassuring for our understanding of structure growth and so on. So this is the one coming from SDSS. So here you have a large sample of galaxy clusters, a few thousands in this case, that was used by Rosso in 2010. So it's at low redshift, but here on this graph, you see, so sigma 8 is the normalization of the number counts, okay, which gives you basically the total number of clusters, okay, and you have the prediction from WMAP in dashed lines, and okay, on the x-axis is the omega m, which means the density of mass, okay, and you see here the contours coming from cluster counts in black, and the ones coming from WMAP. Okay, so here you have, they conclude a very good consistency, even though the error bars are quite large, but they really fall on each other. So this was the status in 2010, where we had the feeling that, okay, with galaxy clusters, we are entering a new era where we can really do, despite the complexity of those systems, the identification of the clusters and so on, we are able to build samples that are reliable enough and are consistent with predictions from CMB. However, things got a bit different when Planck published its first results. So in 2013, in 2015, two papers compared the prediction of CMB and cluster counts. But here, what is interesting is that the clusters they used are the clusters that were detected with the LZ effect. So they are coming from the same data set. Same data set was used for CMB experiment and also for clusters. Okay. So, well, for clusters, if you want to derive estimator mass and so on, you also need to have redshift. So you have a lot of complementary information going on the construction of the cluster sample. However, what they showed here, so I mean, if you compare with the previous slide, you have to look at the values here. It goes from 0.1 to 0.5 and 0.6 to 1. Now here you don't have the same variation, okay? And so it just shows, just to stress that we have much more precise measurements, both on clusters and on the CMB itself, right? And with this, what was found is that there is a disagreement. And this disagreement is at 2.5 sigma, okay? And it shows here on the right side, and on this plot, it shows what they counted as the number, this distribution of clusters, and what they should have counted if they had found the CMB parameters, okay? And it means a factor of 3 different between those two counts. So that's enormous, and this tension has led to a lot of publications since 2013. So you have a lot of studies trying to understand the reason of this tension that maybe was not visible before because the error bars were too large, so everything was consistent. But now that we have precise measurements, it seems to be well, different. So what is the reason? Is it that something somewhere was not calibrated properly? Are there assumptions that were wrong, or simply is there a new physics that is showing up because of this? So these papers, well, until 2019, we had a lot of literature on that. Actually, it's still going on. However, so it's a Bouquet et al. 2019. So in this paper now they used a much larger sample of clusters detected with the SZ effect using the South Pole telescope. Okay, and this dedicated to SZ studies, and there they reconstructed the distribution of the number density of clusters as a function of redshift with the prediction of the lambda CDM model. And now this time you have, they are really consistent with one another. On the right side, you see the difference here between the two, and they are within, I mean, less than 1.5 sigma. Okay, so there is a much larger consistency with this data set. So their conclusion is that that previous studies were not doing a job that was careful enough in terms of calibrating their mass functions, but with this data set and using lensing data with the Hubble Space Telescope, they were able to actually calibrate properly the mass of those systems and recover something that is consistent with CMB and with this lambda CDM model. Okay, more recently, with the dark energy survey, which is we could say a little bit the successor of SDSS, in the sense it's 5,000 square degrees of optical data covering the southern hemisphere. And so the survey has finished this year. It's 6 years of observations. And a first paper came out on the cluster count predictions in 2020. Well, actually, two papers came out in 2020. A first one signed by the whole consortium, and here you have another one that came out more recently. And it's basically more or less the same people, but it was I mean, two papers came in a row, but with different conclusions. The first one basically had predictions that were completely out of what is expected by Planck. So Planck CMB result is this in brown. So it's this guy here, okay? And this has to be compared with their predictions with clusters that were completely off. So here they had calibrations also based on lensing on subset of clusters. And now they redid a new study where they calibrated using SZ information on also a subset of clusters. And now, oops, and now this is consistent at 1.1 sigma, okay, between the Planck CMB and the clusters. Okay, so this shows how difficult it is to this game of the calibration. And well, I think we are only at the beginning. I mean, of course, with clusters, what you want to do is not only to constrain omega m and sigma 8, but our ultimate goal is going to be to try also to infer precise constraints on dark energy, and clusters have the ability to do that if you are able, of course, to calibrate them properly. And I think now with the next generation of surveys, this is something that is going to happen. So we have Euclid and LSST that are going to be launched within a year, and Rosita that was launched recently. And so with these new facilities, we will be able to actually calibrate all our data internally. I mean, so for instance, Euclid is going to be used at the same time to detect clusters, but as it's a space experiment, we will have also data good enough to actually do weak lensing studies and mass estimates directly on the clusters instead of using I mean, a large, different kinds of telescopes to actually calibrate internally. So you always have issues in terms of homogeneity of your data sets and so on. So I think that we are in a position where clusters for cosmology is going to take off. I mean, it took off already, I should say, for at least, a couple of decades, but I think it's going to get to another stage in the soon future. So stay tuned. Well, here I give you, for those who are interested, I wrote here 2 review papers. And well, if you would like to have more information, please write to me, and I can give you probably other references as well if you are interested in some specific parts of this topic. And I think that's what I have.
Thank you very much, Christophe. It was a very nice overview, very comprehensive.
Thank you.
Is there any questions in the audience? But in the meantime, I want to ask one thing. I mean, before coming to the last part, actually, it was in my mind. SPT and ACT, those SZ experiments, do they have better resolution than Planck in general?
Yes, they do.
Okay, so they are not doing follow-up observations of Planck sources. Maybe they do both, but they do fresh new surveys of SC.
Yes, so these observations are being done from especially SPT from the South Pole. Okay,
yeah.
So they have almost space conditions, and they are dedicated to clusters. So the problem of Planck, I mean, Planck is very good, but the resolution is not so good. So it's hard to detect precisely clusters. I mean, you can detect very rich clusters, but less rich, smaller ones, it gets confusing. Okay, so
yes.
These ACT and SPT samples are currently really being used. I mean, these are the ones that everybody now is using with dark energy survey data and so on. So they are becoming the reference.
Okay. Because I had the imagination that Planck is from the space, and how can ground-based radio single dish observations can be better. So okay, now I understood.
Yeah.
So are there any questions from panelists or audiences? Oscar, as usual. I don't know.
Hi, Christophe.
Hello.
Hi, I'm Oscar.
Hello, Oscar.
It's a joke because I usually put questions, very strange questions to the speakers. So
okay.
It's a
Please
joke.
Go ahead.
I don't know, really very interesting. Everything's very interesting. No, I have a question. I don't know if you know these ultra faint galaxies which has quite loose systems, which seems loose, old, sorry, whose masses of the order of 10 to the 8 solar masses. And some of them show a very low amount of dark matter, halo. So there is any explanations of this kind of object? Because in the hierarchical mechanism of formation of the galaxy, as you have explained, in the lambda-cold matter scenario, firstly form a galaxy small object, and then they merge to form a bigger object at a later time. And so this small object could be interesting to support, from one side to support the lambda-cold matter scenario. But then, if they show so little amount of dark matter, they could be a problem instead. So, there is any explanation of that?
Yeah. So, well, first of all, I mean, you have to detect these objects and quantify this, which is tricky. And I think, okay, so there is one point, and maybe I should mention that I have not described in my talk, is it seemed from what I said that cold dark matter explains everything, but it's actually there's a number of issues, and in particular those faint galaxies. I mean, so you would expect still to have a lot of very small objects around bright galaxies. So, for instance, around the Milky Way, we would expect to detect many more small galaxies than what we do. Okay, so that's but this is an ongoing issue. Now, this the point that you are describing in details, I'm not able to answer, but I mean, definitely one of the challenges is to, and I think, I mean, this is actually a science case that is very important for LSST, is to be able to detect very nearby faint galaxies. Okay. For which, I mean, we have added a number of these with a dark energy survey, but with LSST, we really expect to be able to explore much better this kind of regime. So including those very faint objects. Now the relationship with the amount of dark matter is another issue. So well, I'm not expert enough to give you something.
Yeah, as you said, from one side, there is a need of this kind of small object in the current standard model of cosmology. Yeah. But on the other side, we also need 80% of dark matter. So
yeah,
so maybe a problem. So I don't know. It's intriguing. It's an intriguing problem. But for sure, the next generation of instrumentation, telescope like LSST, the Vera Rubin, for sure may, and also the JWST, I mean, may give us more inside, more deep inside this kind of problems.
Yes.
Thanks.
You're welcome.
So thank you very much, Christoph, once again. Thank you. Sorry for the bothering or putting you in a bad situation yesterday.
Oh, no, I am the one apologizing.
We really enjoyed your talk. So I don't know, I think Professor Orhan and Ayşegül can take over if we can proceed to the closing ceremony. Are you here? Available?
Yes, we can. Just give me a few minutes.
Sure, sure, okay.